would like to thank the organizing committee to invite me to give a talk here to celebrate my brother's 75th birthday. So my talk here is on the high-order Jacobian matrix theory. This is motivated from the high-order Nash-Bohr up. This you will see later. Okay. So this high-order Jacobian matrix involve any high-order derivative. So from this, we will construct many invariants of the singularities involving high-order derivative. This is the first time because all the previous invariants are involved the first derivative. And also using this high-order Jacobian matrix theory, we can construct the inverse of a mapping. So we will see that also later. And also we will improve the we will look at the finite determinacy of the power series that will dramatically improve the classical theory also. So this overview of my talk. So this is the this is the notation. S is a power series ring, the maximum ideal N, and R is also power series ring. M is the maximum ideal. ON denote the convergent power series ring. And the map between two rings is actually preserving the send maximum ideal to maximum ideal. And this is the classical notation. We use this classical notation also to make theory easier to be understood. So you take a Taylor expansions. So basically you so you get this formula. So we will so the Taylor expansion here up to order k, and for and we need also notation that we forget about the C order term. So we denote TL upper circle. That means we forget about the C order term. So we will think of it as a column vector. TLKF is just a column vector like that, and you throw away the TLK upper CO means you throw away the C order term. So we define the kth order Jacobian vector Jacobian matrix is for any A. I mean A is a vector here. Okay, with order less than k minus 1, and for B, and this is the strictly balancial. And the AB entry of this vector Jacobian matrix is defined by this. For B, you have a natural order here. Use a natural order, and it's 0 otherwise. So that's the matrix. So similarly, you can define. So I should point out that this one is not a square matrix. This is not a square matrix. Now we define the kth order P quasi vector Jacobian matrix. Now this one is is a square matrix because we take all the A include up to all the K and including C and B also. So the AB entry is exactly the same as before. And since you're like, this is also the partial ordering, the usual partial ordering. And then if you use the lexicographical order, then this so we call it P quasi vector Jacobian matrix is actually upper triangular. So for example, you look at the two variable case. So the vector Jacobian matrix is not a square matrix, it's a matrix of this form. And the P-quasi vector matrix, Jacobian matrix, is a square matrix of this form, is triangular, upper triangular. So you can show that you have a so-called Leibniz rule. You take the Taylor. This is a vector form of this F times G is actually equal to vector Jacobian matrix transpose times this Taylor expansion up to K minus 1 order of G. And the Taylor expansion up to K order of F times G is actually equal to P quasi vector Jacobian matrix transpose times this TLKG. And also you have this equality. They actually equal this. So this is an example. We compute it so you can understand much easier to illustrate the formula you get. And for the product, you have the product rule like that. So that's why it commutes. So this matrix actually commutes. Now we consider a chain rule. So phi is phi is the mapping from R to S. You send yi to hi. Hi is in the maximum ideal. Then we define the d phi up to all the k is actually just take the Taylor expansion k circle with phi. So more precisely, you just send yi to the Taylor expansion of hi, and we use the notation the pi a just a project. Pi a is just a projection operation, projecting the a coefficients. So we denote the transformation Jacobian of phi up k order. We call it T Jack K phi. So it's labeled by the multi-index for B. We take out the constant, the C order term, the CO terms, and also A is you take out the C order terms. So the BA entry is just the BA entry is just the projection of d phi up to order k acting on yb, and the at jk phi, we call it the associated transformation Jacobian. It's the same, but you include the CO term here. So for example, you have mapping like this. You send y1 to f or y2 to g. Then the transformation Jacobian of phi is given by this matrix, 5 by 5 matrix. And the associated one is just get one more square matrix. So the chain rule, we can compute a chain rule. So you have, say, G is element in R, phi is mapping from the ring from R to S. Then you have this formula, phi of the P quasi-vector Jacobian matrix of order K of G times this associated transformation Jacobian of phi is actually equal to the associated transformation Jacobian of phi times the PQV of ZK phi G. If you have another mapping from say first from R to S and then S to U, then you have this chain rule written down explicitly. And also you have the chain rule for the associated transformation group also. So when M equal N, the size of this associated transformation Jacobian is N plus K choose K. You have such a good property that the determinant of the associated transformation of ZK phi is actually equal to the usual Jacobian matrix, classical one, raised to power N plus K choose N plus 1. For example, you look at this two, Jack 2 phi, AT Jack 2 phi, you take the determinant is given by this power. Determinant of the classical matrix raised to power 4. So we develop this theory is to get high order invariance. So the classical one is just the Mueller algebra involves the first derivative, and the modular algebra, or sometimes people call it Turiner algebra, also involves the first derivative only. So this in the isolated singularity, this is called the Mueller number. The dimension of MF is the Mueller number. This Turiner algebra dimension is called tau F, the Turiner number. Or so we say that let us recall that two functions called right equivalent. If you can change coordinates such that you change coordinate, then these two functions becomes equal. If they are called contact equivalent, if you change coordinate up to the unit element, U is the non-zero invertible element, then they are called contact equivalence. The contact equivalence is considered by algebra. So you want to so that means that they are biological. So the variety divided by F and G are biological equivalent. The Yau theorem says that if you are interested in the contact equivalence, then they are actually you only need to consider the algebra. For all B billion equal 1, this algebra is isomorphic, or if there's some B billion equal 1, this algebra is isomorphic. So all these are equivalent. So that's why this algebra is interesting. Now, so all this the previous things that involve only the first derivative. Now here we generalize the we look at the higher order Jacobian matrix, right? This is we look at the ideal. So this V I R K F is all the R by R minus of in this vector Jacobian matrix of order K. Take all R by R minus, and you take the formal passes rank chosen by F together with this all R by R minus in this vector Jacobian matrix. So this from algebra, and you can also consider similarly instead of vector Jacobian matrix, you can consider the P quasi vector Jacobian matrix. You take the R by R minus, and you do the same thing. You chosen by this all R by R minus. Okay. So this is type 1, type 2. Similarly, you can define this corresponds to the generalized Müller algebra. This generalized Müller, you take the R by R minus in this transformation Jack KF. You take the quotient, there's type 1, and then type 2 is you take the R by R minus of this associated transformation Jack KF. A quotient by that, that's generalized Müller algebra type 2. So all this involves the high order derivative. So our main theorem says that this this algebra I just defined generalized to linear algebra type 1 and generalized to linear algebra type 2 are contact equivalence. That means if two functions are if the variety are parabolic equivalent, then this algebra are isomorphic. So this number, if finite dimensional, this must be invariant. So we introduce, so both type 1, type 2 are invariant. So actually, in our paper, they are more generalized to linear number than the type 1, type 2 I show in here. So for simplicity, I only show two of them. So for example, you look at the for n equal 2, so you get a favor on this. So the type 2 generalized to linear number of type 1, you just because this algebra modulo the 3 by 3 minus of this matrix, 3 by 3 minus of this matrix. Okay, and then you get a new invariant there. So there's a high order derivative involves second derivative. And you look at the you see this one. You look at P quasi vector Jacobian. Then you can for any L, between 1 and 6, you can look at the L by L minus of this determinant, and quotient by that you get a type 2 generalized Taylor number. So you have a lot of invariants associated with this. So this one is you see you can take for two variable, you can look at this algebra quotient by this 3 by 3 minus f times 2 by 2 minus and f squared times 1 by 1 minus in this reject 2. This is also invariant. So this is different from what we just said. So there are a lot of more invariant we can construct involve high derivative. So the similar thing happens to the Milnor algebra, the generalized Milnor algebra. Generalized Milnor algebra are right of type 1 or type 2. They are all right invariants. For example, you look at this type 1. You look at of the two, you just take 2 by 2 minus of this matrix. I did generate by 2 by 2 minus matrix and quotient by this. You just take the formal partial string quotient by this 2 by 2 minus. So it's Y equivalent. Type 2 is you just take 2 by 2 minus of this matrix. So they are also Y equivalents. So in this way, you construct a lot of invariants. So actually the motivation is coming from Doherty, the Mexican mathematicians. He first considered the K-order mass rolling up of hypersurface. He found out that you couldn't consider the matrix divide. He denoted this matrix divided by the ideal IKF, then maximum minus of vector Jacobian matrix of F. And actually, we look at we did the case for n equal 2, and in 2020, and then we find out that this can be done in general for any dimensions. So now how about finding the inverse? So we can divide for any mapping from R to S, there's a natural mapping from the KJ, associated KJ mapping. And the matrix associated to this VK is given by this. So assuming that the determinant of Jack phi does not vanish, then we have the form theorem. The matrix associated to the VK is actually what we define, what we just defined, transformation Jack K without a zero. So in particular, if phi is invertible, then you get this identity. So for example, you want to solve a system. So assuming that the left upper left corner, the determinant matrix is not zero. So by implicit theorem, you should able to find a system of solution of this form. Now theorem says that you can do it in this way. So you send yi to gi if I is less than equal to m. Then the inverse is given by psi here, by psi explicitly given by here. For k, if k is greater than equal to 2, then the transformation Jacobian of psi is equal to transformation Jacobian of phi inverse evaluated CO. So we said so for VMD you just said for Fy in VMD we said Hi to be Fy evaluated the first m variable evaluated CO. Then we see that this is actually the unique solution of the system A. And for any k explicitly, H1, this H1k, HMk can be obtained from matrix, transformation Jacobian matrix. So that means we can find the inverse quite explicitly. So for example, you look at this system, so you see that the 2x2 matrix determinant is not zero. So you can compute this inverse, T Jacobian inverse, and from this first two rows, we can write down F1 and F2 explicitly. And you see, we obtain the formula H1, H2 by evaluating the CO. The first two variables equal CO. Then we get the second order approximation of solution explicitly. And this can be any order. You can do it. So the last application I want to say about is the right determinant. I mean the finite determinacy. So we say that two functions are right out determined if Fr equal to TR implies F is right equivalent to G. The minimum R is called the right determinacy of F. Okay, so you can do the same thing, same notation for contact R determinacy. Similarly, the classical theory says that if F is right determined, then maximum ideal raised to power R plus 1 is contained in M squared times the Jacobian ideal. And F is contact R determined if MR plus 1 is contained in M squared times the Jacobian ideal plus M times F. So following now theory actually looks much better because if you take S bigger than equal 2 and F is any formal power series ring, any formal power series satisfy the order is at least 2, then MS plus R equal to the R order of F derivative and Jacobian ideal of F R order times MS plus 1. Then it's R plus S minus 1 determinant. So of course, it doesn't matter whether this is convergence. If this is a convergent power series ring, it's the same, because you can use active analytic approximation theorem to get the same statement. You see, for example, this functions, this convergent power series ring, according to the classical theorem, this is right 5 determinant. But using our theory, we can show that it's actually right 3 determinant. So it's much lower. And this function, using classical theory, G is right 10 determinant. But using a theory, you can say, in proof theory is four determinants. So that's basically that's all I taught here. So the point here is that this is the first time we found a lot of invariants involving the high order derivative. That's the first time. So presumably we can use this to prove the Jacobian conjecture, at least in two variables later. So because we can find the inverse, we hope we can find the inverse, give a constructive proof and find the inverse explicitly. Thank you.
Any quick questions? Oh, no, let's thank Professor Yau. So we're running late. The next talk will start in 5 minutes.